This video tutorial is meant to explore some of the nuances of rounding a percent error problem. We have looked at how to calculate percent error, and we have looked at significant figures and how to round answers using significant figure rules, but now we're going to put those two things together. So we have seen that percent error is defined as the measured value minus the accepted value, all in absolute value. So we'll take the positive number there and we'll divide it by the accepted value. And then we're going to multiply the whole thing by 100. Now we may have used different terms in class. The measured value was typically the student's measurement, and the accepted value, sometimes we refer to it as the official value. So if those words make more sense to you to use for this equation, then that's maybe helpful. So what's interesting about a percent error problem is that we have mixed operations here. We have subtraction going on in the numerator, and answers to subtracted answers have a different set of rules than multiplication and division. So in this problem, we've got subtraction in the numerator, and then that answer is then going to be divided. So we're going to do percent error problems as two-step rounding. We will round the numerator according to subtraction rules. We'll take that rounded answer and divide by the denominator, and then round according to division rules. In the example, you can see that the student's measured value is 9.73 meters per second squared, and the known value, the accepted value, the official value is 9.80 meters per second squared. And so when we subtract those two numbers and take the absolute value, I'm going to reverse it so it's a little easier to see the math. So 9.80 minus 9.73, we can see here that both of those numbers are to the nearest hundredth, so we have to make sure that our calculated answer is to the nearest hundredth, right? So remember, we're cutting off our answers right there. So that's why the numerator here is to the 0.07, okay? So that is correctly done to the nearest hundredths, but what the result is when you go to divide here, right, when you go to divide those two numbers, you're now dealing with one significant figure in the numerator and three significant figures in the denominator. So that's why in the end your percent will only have one total significant figure. So of course the next thing we have to do is just try a few examples. First example here, a student measures the density of an object to be 8.73 grams per milliliter, but the accepted value is 8.96 grams per milliliter. What is the student's percent error? So if we take the measured value, the student value of 8.73 grams per milliliter, and we subtract from that 8.96 grams per milliliter as the official value, put those in absolute value brackets. We're going to divide all of that by the accepted value of 8.96 grams per milliliter. And we're going to see that the numerator, the difference of the two numbers in the numerator, is 0.23. Both of these numbers are to the nearest hundredth, so our subtracted answer here needs to be to the nearest hundredth. So we're going to take that 0.23, that unit there is grams per milliliter, and we're going to divide that by our accepted value of 8.96 grams per milliliter. Of course, in the end, those two units will cancel, and what we're going to do here is divide 0.23, which has two significant figures. We're going to divide that by 8.96, which has three significant figures, and in the end, this rounds, and that will, can't forget, multiply by 100, and this is going to round out to 2.6%. Another example, number 2, a student weighs an object to 65 grams, but the accepted mass is officially at 55 grams. What is the student's percent error? So we're going to set this up as 65 grams minus 55 grams, absolute value brackets, and the official value, the accepted value, is 55 grams. And of course multiply by 100. So we are going to do the subtraction first. 65 minus 55, of course that's 10, But because both of these numbers are to the nearest whole number, we want to make sure that our subtracted answer of 10 is also significant to the nearest whole number. Therefore, you either need to put a decimal or you need to put a 10, a bar over that ones place. I'm going to use the decimal method. All right, so we've got our numerator at 10 point to indicate that it is significant all the way to the ones place. And of course that's grams. We're going to divide that by 55 grams and multiply by 100. So now we are looking at 2 sig figs divided by 2 sig figs. So our answer should be 2 sig figs. And so that's going to round out to 18%. Our third example is a student measuring the volume of an object to be 6 milliliters, but the object is actually 5 milliliters. So 5 milliliters is going to be our official measurement. The percent error is going to be the difference between those two, 6 milliliters minus 5 milliliters, absolute value brackets, divided by the official, the accepted value of 5 milliliters. So here, our subtracted answer, first of all, make sure we don't forget to do the times 100 part. Our subtracted answer, 6 minus 5, of course, is 1. We have the correct number of sig figs here because 6 and 5 were both to the nearest whole number. And the subtracted answer of 1 is also to the nearest whole number, so we're good to go on that. That's going to be milliliters. We're going to divide that by 5 milliliters, right? So the milliliters are going to cancel, and 1 divided by 5 is going to give us 20%. And we want to make sure that we are only showing 1 sig fig because we had 1 sig fig in each of our measurements. If we just write the answer at 20, and so no decimal, no bar, we're going to have just that one significant figure in that 20%. And so there you have it. So those are some of the weirder significant figure issues that can happen when you're rounding a percent error problem. All right, we'll see you back in the classroom. Thank you.